right. Well, welcome everyone, both in the room and online. It's a really great pleasure to have Subhro Guhathakurta be our webinar speaker today. Say that 10 times fast and you get the prize. But Subhro is a Harry West Chair Professor in the School of City and Regional Planning and Director of the Center for Urban Resilience and Analytics at Georgia Tech. I had to read that. I don't have it memorized, but he's, needless to say, big man on campus, as we call it. He came to us a few years ago from Arizona State, so there is a connection to longtime friends at Arizona State. He there was the Associate Director of the School of Geographical Sciences and Urban Planning, as well as a founding faculty member of the School of Sustainability. He co-edited the Journal of Planning, Education, and Research from 2011 to 2015, and is serving on editorial boards of several leading planning journals, including associate editor of the Journal of the American Planning Association. So the planners in the room know that those are like the two best journals in the field. Professor Subhro, as we'll call him, has published widely in many planning domains, including energy systems, urban heat, sustainable development, travel behavior, housing affordability, integrated urban models, built environment and health, and the use of geospatial technologies in urban planning. At least as importantly as that, he's a great scholar, a wonderful person, and a wonderful colleague and friend to have. So we're delighted that he's giving us the webinar today, and I'll turn it over to you, Subhro. Thank you very much.
Well, thank you, Pat. Well, it's a real honor to be introduced by Pat. And I'm delighted to see so many of you here. And thank you, everyone, for joining in from across the globe. So I also need to thank a few other people. First of all, I want to thank the sponsor of this project, which is the National Center for Understanding the Future of Travel, Behavior, and Demand. And also the logistics of this event was coordinated by several people, including Irfan, Batur, Ram Pendiala, Pat, of course. So thank you all for making this event happen. Thank you for the lunch that you're providing for everybody here. And most importantly, okay, now my thing is not working. All right. Most importantly, I want to thank my fabulous team. So if you find this presentation, the information to be valuable, the kudos go to them because I stand on their shoulders. I feel like I am the orchestra conductor who doesn't play an instrument. So yes, I'm really proud of this team. Sung-jae has been one of the coordinators of this project, and he's worked on sidewalk width detection, which I'll share with you. Cheon has been working on pedestrian detection and tracking pedestrian flows. Jay Gon has been working on-street parking detection, which I can share. Bryce has been looking at bus stops for MARTA buses and whether they have shelters and other amenities using Google Street View, and he came up with a very ingenious way of automating that process. Subhro has worked on transit accessibility and how to score transit systems. And UJ is one of our former graduates, former PhD graduate, and he's now working with ARC as a collaborator. And particularly the on-street parking system was initially designed by him. So that's the fabulous team. Let me talk a little bit about the motivation for this work. Many of you know that our previous work has involved a lot of studies around walkability, walkable environments, pedestrian zones, and how pedestrians feel in different kinds of infrastructure, built environments. And then we also did a lot of work on biking infrastructure, essentially looking at safety of different types of bike infrastructure. And that was also the PhD thesis of UJ, who I mentioned earlier. So the reason why we are now thinking about complete streets is because we wanted to put all of these different elements about walking, biking into the street environment. And when you put all of these in the street environment and you're trying to understand the entire right of way of the street, you come up with this idea of a complete street. And this idea has been around for at least 20 years. And what complete street suggests is that we want to encourage multimodality in transportation. So encourage as many modes, including active travel. We want to especially enable active modes such as walking and biking. And ultimately, we want to make streets safer for everybody. And when we talk about everybody, we are talking about all age groups of people and people of all abilities, physical abilities, economic abilities. So how can we build streets that are complete? So we have a lot of streets. Some they claim are complete, others may not be complete, but are still claimed as complete. So I have 4 images, street view images of streets. Can you spot which one is the complete street? Anyone? That's, yeah.
Maybe the top right.
The top right. Okay. So let me tell you, all of them are considered complete streets. And the reason why we wanted to do this project is because, you know, we don't really have a measure of how complete the streets are. Any elements that you put in the street, if you put a bike lane in it, if you have a pedestrian zone, you might call it complete, but it doesn't really function as well as safely for everybody. So how do we develop a method, a scalable method to score the completeness of streets? Now, as I said, complete street has been in the policy domain for a long time. And there is this organization called Smart Growth America that has been tracking complete street policies over the past 12 years or so. And you can see 36 states and territories, union territories, have already adopted complete street policies, including our state, Georgia. So we also have a complete street policy in place at the state level. And also there are separate complete street policies at the county and municipal levels as well. So the goals of this project, as I was explaining earlier, is to develop a scalable and replicable approach to document street assets. And we want to do that using data that are ubiquitous and comparable across cities, because if you are going to develop a measure, then it has to be comparable across different cities. And we want to create a scoring system to assess the complete street assets. And ultimately, we want to develop this dashboard to provide access to all our tools, because if you have these tools, and if other cities, other counties want to find the completeness of their streets and compare with streets across the country, they can do that using our tools. So that's those are the goals for this project. So this is an image of complete street, which apparently was generated by either ChatGPT or one of the AI generated images. So there's no copyright infringement here. And you can see the various elements of, so the street buffer is an element, the sidewalk is an element, street parking. So these are all various elements of complete street. And what we are concerned about in this project are these particular elements. So we want to look at the width of sidewalks. And if you are looking for that data, very few municipalities maintain that data. So we are trying to figure out a scalable way of finding the width of sidewalks. We are also concerned about bike lanes, obviously, transit stops, street parking, sidewalk buffer, median, vehicle lane, and various points of interest along the street. So these are the elements that we want to score. We want to first detect, measure, and score in our overall scoring of complete street. So in today's presentation, we have all these elements that we have been working on. Now, the issue that I've found is I can't really present all of them. I have 130 slides, and each one of them are pretty involved. So I'm going to ask you to tell me what you would like to hear about first. And we'll take about 30 minutes to see how many of these we can go through from 1 to 5. The pedestrian tracking I'm keeping out because that was a slightly different project, although related, but not quite in the complete street. And then I will also talk about how we weigh these different elements. And then finally, I'll share the rudimentary website that we have created. Of course, it needs further development. So any takers or anyone wants to propose what they would like to start with? We can start with. We can start with the sidewalk width or bike lane, or those two are pretty complete. The sidewalk is also published, recently published. Bike lane, we have reviews, and we are preparing to, yes?
Online votes for number 3 and number 1.
Oh, POI accessibility and sidewalk width. Okay. Why don't I start with the sidewalk width? Because I think that will get your juices flowing. So, and then I'll go to POI accessibility. All right. So, how do we score sidewalks? Now, we all know that sidewalks are important, especially for those of us who are concerned about walkability and the pedestrian environment, and it improves the overall livability of urban areas. And we know that getting information about sidewalks is very labor intensive. So far, there has been very few techniques, methods available through which you can get sidewalk widths that are scalable, that can be done quickly. We do have some computer-based digitization methods, but even those are manual digitization methods. So you might think of a satellite imagery or a video that are then used to extract the information of sidewalks. So there is a process of looking at these images and manually digitizing. So recent advancements, which is what we use in computer vision, with aerial imagery, but we don't use aerial imagery, have enabled the automatic detection of mapping of sidewalks and other pedestrian infrastructure. The problem with aerial imagery is that we often face occlusion. You have tree canopies that cover sidewalks. You have shadows of various buildings that might make it difficult for the computer vision algorithm to pick out sidewalks. There is, of course, this open source tool called Tile2Net, which was designed by Mariam Hosseini, who is now assistant professor at UC Berkeley in the School of Planning. She did this when she was in New York, and she also was a postdoc at MIT. So the limitations, as I was saying, because sidewalks have a small visual footprint, it's challenging to train image data sets to recognize that small footprint. And of course, it can be hindered by occlusion, shadows, vegetation, and urban structures. And visibility and accuracy are sensitive to variation in sunlight conditions. So you have to find the right aerial image and the right time. But it might be right for certain areas, but not for other areas. And also it requires very high resolution satellite imagery. So our approach is to estimate both sidewalk presence and width using just street view images. So we decided, and I'm glad Sung Jae figured it out, that we will only use street view images, which I believe is fairly ubiquitous, although it varies in terms of its temporal frequency, how often these images are taken by different cities. Although a lot of cities, even in the global south, have Google Street View images, but the temporal frequency of those will be lower. But then again, sidewalks are not changing dramatically year to year, right? So if you have good street view imagery of 1 year, you can expect them to be more or less accurate a couple of years down the road. So we use Google Street View and do two types of segmentation. One is a semantic segmentation using computer vision, that is to define where the sidewalks are. But we also have to figure out where the edges of the sidewalk are. And as I'll show you when I go through the method, the edges are very critical, how we define those edges. And after we extract the sidewalk edges, we use trigonometry by using the pitch of the camera angle to determine the size or the width of the sidewalk. So let me explain how this is done. So first of all, we use two parameters of the Google Street View images. One is called heading, which is which direction the camera is pointing, and we have to make sure that the direction is perpendicular to the sidewalks and the road is parallel to the sidewalks. And the second parameter that we use is the pitch, that is the tilt of the camera. And this pitch is very critical for our purposes, as you will see. So we use the heading to be aligned to the road direction, that is, it has to be parallel to the road. But essentially, we are looking perpendicular to the road towards the sidewalk. And this diagram shows you how we are taking this three-dimensional environment. It's a three-dimensional built environment. But when we capture it on a street view image, it's a two-dimensional image, right? So the whole process of taking that image from a three-dimensional form to a two-dimensional is critical here. So the variation in pitch value affect the projection of the sidewalk on the image plane. So the pitch value in this case is very important. And the pitch values can be negative or positive. So if the camera is looking up, then the pitch is positive. If the camera is looking down, the pitch is negative. So the technique here, the method that is used is to align the pitch of the camera to the top edge of the sidewalk first, and then again tilt the camera again to the bottom edge of the sidewalk. So you have two pitch values, one for the top edge, one for the bottom edge. And once you know what those pitch values are for the top edge and the bottom edge, then you can use pure trigonometry. You know, this is what we have learned in high school, that is taking BC is essentially the distance between B and G minus the distance between C and G, and you can use trigonometry to figure out what the size of the sidewalk is, right? So sounds simple enough in theory, but how do you actually figure out what these pitch values would be? And since we are trying to automate this process, so how can we efficiently find out these target pitch values? Because we cannot manually tilt this till we see when it is aligned to the top, and then tilt it again and see when it is aligned to the bottom. Because if we do that, then the whole goal of this project of having a method that is scalable and replicable goes away. So we have to figure out an approach to know exactly what the pitch values should be and automate it. So the way to do it is to first use semantic segmentation to know where the sidewalks are. And then we do this scanning edge detection. And I know Sungjae tried many different types of edge detection algorithms, and this one turned out to be the most efficient. And then we extract the sidewalk edges. And when we extract the sidewalk edges, we extract it every 10 meters. So that there are places where the sidewalk is wider because of curbs or driveways, and places where they're shorter. But if we do it every 10 meters, then we can know which one, where is the consistent sidewalk. So this is the segmentation, the first step. That is how we do the segmentation using the SegFormer V5 semantic segmentation model, pre-trained on the cityscape data set. And then using the segmented image, we apply scanning edge detection to extract the sidewalk edges. So now the question is, how do we find the target pitch? So if you think about the target pitch, it is the pitch that is based on this constant R. And this R is essentially the focal length. That doesn't change. Even though the pitch might change, but the focal length of the camera, because the camera is stationary and it is not changing its focus field of vision. Therefore, the focal length is the same. And you can figure out what this target pitch is if we know what this constant is, right? The constant is essentially that distance. So the way to derive this target pitch is to use two different pitch values. The first pitch value is 0. And we figure out what the pixels, the number of pixels that it is away from the center using 0. And then we use a pitch value of -10. Actually, you can use any pitch value. It doesn't matter as long as it is consistent. But you don't want to use a pitch value that is too high because then you'll miss and then you figure out the distance between the center and the edge, the top edge. So you have two images essentially. The first image with one pitch value and the second image with the other pitch value, the 0 degrees and -10 degrees for the top edge. So you are looking at the distance from the top edge to the center of the image. And when you divide the two, you get a ratio which we can then translate into the target pitch value. And this is done using the fsolve function from the SciPy optimized module. Now, don't ask me how this is done because when I read it up, it seems like it does a lot of numerical algebra. And, some of you are nodding your head, so you probably know how they do. It's an iterative process through which it finds the target pitch value. But thankfully, we have this algorithm, the fsolve function, which generates this pitch value automatically. And we do the same for the bottom edge of the sidewalk. So we go through the same process, get two images, first at pitch value of 0, second at pitch value of -10. But this time we are more concerned about the bottom edge. We do the division of the two pixels and use the fsolve function to come up with the target pitch value. So once you know the target pitch value for the top edge and the bottom edge, then you can, put it in your code to figure out what the sidewalk width is going to do. So we put the two pitch values and the height of the camera, which we assumed to be 2.5 meters. There was some I would say, debate about what that height is, because Google does not really publicize that height from which this camera is taken. So we had to scour the internet to find what this height could be. And several other researchers have used 2.5 meters. So we thought it would be a safe one to use. But we, of course, validated it. So we did a lot of ground truthing. We did the ground truthing here in front of our research center. And also we did ground truth with a very robust data set of sidewalks, which was available to us from DC. So it's publicly available, and the city of Washington, DC has done these measures. So we use this, at least a small sample from the DC sidewalk, to figure out what the errors could be. So we validated our method. We found the error is about 0.32 meters in terms of the average error of the technique we were using. And then, of course, we were wondering about what could be some of the ways we can make it even better, and what are the sources of error. So the first source of error is because of the variation in curb height. So if the curb height is not consistent, and we have assumed a certain curb height, then you might get some errors. Because when we do the semantic segmentation, the curb height is included in that segmentation. The second source of error arises when the sidewalk is located directly adjacent to the street. So when it is directly adjacent to the street, then the curb is sometimes included into the segmented sidewalk. So if the sidewalk is 2 meters, then the curb in the image, the segmented image will be added to the 2 meters. It will become 2.2 or 2.3, depending upon where the camera is. So in that scenario, the segmentation model may falsely detect the curb as part of the sidewalk. So if it is very close to the edge of the curb, then there might be some error introduced. Another potential source of error relates to the field of view setting used when retrieving street view images. Sometimes if the field of view is too close or too far, then this might fail. But we have tested it for many field of view. There is a range of field of view within which it works quite well. It's only when it is well beyond that normal range that it might fail. And lastly, the use of the solve function to estimate the targeted pitch could introduce some errors because this function is an iterative function. And if you run this function many times, it will give you slightly different results each time because it is doing some numerical analysis. And therefore, those errors might propagate across the width point. So that's all I have for sidewalk width estimation. So let's go to the next one. You said POI accessibility. This will be hopefully, oops. Let's go back. Okay. So accessibility to points of interest. Now that's a very, I would say, important aspect of livability. People are on the street, on the sidewalks, because they want to access some activity centers, places that they want to visit. So these points of interest, if we have more points of interest, it livens up the street. So we wanted to score these points of interest. So we got data about these points of interest locations and their operating hours, as well as their NAICS codes. And this data is available from many sources right now. Point of interest data you can get from Dewey, you can get from Google. There are many vendors that will provide you with point of interest data. The tool that we are using is here routing API to generate walk sheds. So we generate a walk shed around each point of interest, and these walk sheds are about 700 meters. That's what we define as a walkable distance. And the output is an accessibility score for each road segment. So we average out the accessibilities of each POI and then generate the score for the road segment. So generating walk sheds is a simple GIS process. That's I'm not going to talk about that. Assigning weights and values to POIs, that's an important process, and I want to show you the kind of attributes of each POI that we use to assign those scores, and then I'll show you how we aggregated them. So I have to go a little faster, I think. So we assign weights to POIs based on the amenity type. That is the type of amenities, the amenities that people actually want to go to or visit more often, and the number of operating hours per week. That is how long they are open. And for amenity type, we look at the popularity and intensity of amenities. That is, how long people actually stay in those places. These are the 10 different, 10 different types of services, and you can see the different NAICS codes for each of those different amenity groups. And these are all based on our reading of the 15-minute city literature. So if you go to the 15-minute city literature, it talks about the kinds of amenities that they want to have within the 15-minute walk share. So we looked at raw visit counts, that is how many people visit these POIs across the country. And you can see that we're looking at these 10 different types of activities. We also looked at how long people stay in those different types of activities. That's the average dwell time. And we looked at the mean operating hours. And that's how we came up with our weights using the the road segment. The road length was one of the key attributes that we used. Number of POIs of that road segment and the weight. And the weight assigned to each POI was based on the various features of that POI that I shared, like how long people stay, how attractive it is, how many times people go there. So that is about the POI score. What next? Bike lanes. Okay, let's go to bike lanes. Well, that will be probably the last one because I have to move on. All right, bike lane detection. So here the input is 2 Google Street View images with 2 opposite headings. That is, one looking on one direction of the street, the other looking at the other direction of the street. And then we also use a satellite image, a Google satellite image. So we developed this image classification model in-house. And this is also something which Subhrajit has developed. And the bike lane type that we are trying to classify is whether there is a bike lane present, yes or no. If there is a bike lane present, is it designated? That is there a designated lane for bikes? Or is it protected? That is, does it have a barrier between bikes and other vehicular traffic? So we have these 3 types of information that we are looking at. Street view imagery A looking in one direction, imagery B looking at the other direction, and the satellite imagery. So what we are trying to do is trying to figure out what kind of model works best in classifying types of bike lanes. That is the 3 types of bike lanes that I just mentioned. And to do that, we use 6 different types of models. And these 6 types of models is based on how we merge the information coming from these different modalities and at what stage. So there are 3 different decision points that we used for these 6 models. And I'll show you exactly what we mean. The first is which modalities are concatenated at which stage. So in the mid stage, if we have street view features first, then combined with satellite. So we first combine their 2 street view features and finally combine with satellite. That's one way we can predict the presence of different types of bike lanes. The other is late stage, that is, each modality processes information independently. And then we do the fully connected layer at the end. So that's one decision point, right? Those are two different models. And then the second decision point is the fusion level. So features from each modality are blended into a single joint representation before classification. That is, before we classify it, we join the representation together, or we separately classify them and then figure out what the best classification is based on these individual classifications. And finally, the label structure, that is, are we classifying bike lanes directly as protected, none, and designated, or do we do it in a hierarchical form? That is, first we decide whether a bike lane exists or not, and then if a bike lane exists, only then we classify whether it's protected or designated. So those are the three different types of decisions that we tried to make for, which led to 6 different models. So we had several images that we collected to train this model. We had 526 samples of designated bike lanes, 238 samples of protected bike lanes, and over 1,000 samples of street without bike lanes. We did some upsampling using these images. And then finally, they arrived at this classification models. And remember, we did 6 different models. So we are testing the parameters of all 6. And I'm just going to go quickly through how we actually use these images, what kind of images that we use for designated bike lanes versus protected bike lanes. These are some examples of images that we use. This is for designated bike lane. This is for protected bike lane. Just some examples. And then finally, the results. So you have these 6 models, and you can see the concatenation stage, late or mid, fusion level, whether it's at the feature level or decision level, and then whether the label was flat or hierarchical. And we finally ended up with the last one, which is hierarchical, decision level, and late concatenation, which gave us an accuracy of 0.9, precision of 0.89. So we thought it was a pretty good model to go with for detecting bike lanes. All right, so that's bike lanes. I think I'm going to stop here because, but those other 2 are also very interesting. But I don't have the time to go through all of these other elements. Let me talk a little bit about weight assignment, because I thought this was also quite ingenious, because we use other tools to do the weight assignment. So the question here is, how much does each complete street element contribute to the benefits of complete street policy? Okay, so, and what do we mean by benefit of complete street policy? And the tools that we are using is a zero-shot classification model using natural language processing, and then, of course, using some large language models. And I'll show you exactly how we are doing that. And then the output is the weight of each element. And there are 8 elements of complete streets that we are tracking, and we want to find the weight of those elements. So each of these street infrastructure, which would be our elements of complete streets, we want to connect with these benefits: safety, environment, livability. And the way we decide on what these benefits are is based on this document that we came across, the best complete street policies. And in this document, we found these 5 benefits for complete streets. So you have community, economy, environment, health, and safety. And our objective is to figure out how each element of our complete street infrastructure is related to each one of these benefits. So these elements might be related to more than one benefit. And how do we do that? So we want to first of all figure out whether the sentences that we derive from these policy manuals relate to any one of these benefits. But we also want to know how confident this relationship is, how confident we are about this relationship. And this is the workflow. It's a very complicated workflow, but I'll try and go through it in small bites. So the first thing we do is collect municipal level complete street design manuals, and we collected 73 complete street design guidebooks from 58 cities. 5 of them were from Canada. Then we did some text pre-processing and we extracted sentences containing the key complete street elements. And this text processing was not easy because you have different kinds of documents, different layouts, different PDFs with sidebars and tables and charts. So we did find an algorithm that's available online to figure out how to extract it. I think Subhro actually did this part, right? Yeah, Subhro figured out how to get the text out. And then we extracted the sentences that relate to each one of these elements. So we had 25,252 sentences from these design manuals. And then we had to evaluate these sentences for the goals. And these are the 5 goals. And for each one of those 5 goals, we had 2 benefits. So, for example, for community, we had fostering vibrant public spaces, increasing opportunities for community member participation in the transportation planning process. And you can read what those different benefits are for each one of those keywords. So we use prompt engineering using a large language model to understand what each sentence says about each street element. Okay, so we had to figure out whether the sentence has a particular tone, and also whether the keyword in the sentence was aligned with the elements of complete street. And assessing the tone, we use this 4 forms. One is normative, prescriptive, descriptive, and technical, which is somewhat aligned with the way we learn planning theory, because in planning theory, we often talk about normative, descriptive, and procedural theories. So our tone is going to be based on these 4 different types. And the technical tone is the one that we ignore, actually. We only work with the top 3, normative, prescriptive, and descriptive. We are not so concerned about the technical tone. So we want to specify what the keyword is in the context. For example, the prompt is, you are a keyword detector, decide whether element, and this element could be sidewalk, could be median, it could be bike lane, is used as a keyword in the sentence. And the result is a binary yes, no, yes, it's a keyword, or it's not a keyword. So we know the tone and whether it's a keyword or not using the LLMs. And we extract these sentences per element. And using those sentences, we identify the benefits described in those sentences. So now we have to figure out what benefits do they align with? We know that these sentences are about those elements of complete street, but how are they associated with the benefits? So we use the zero-shot classification models for this. And a zero-shot model is essentially a model that doesn't need any training. And we use natural language inference. So finally, we come up with generalized knowledge to make inferences about new categories based on a given text without the need for labeled examples. And what we get are these sigma scores of various benefits. That is, we get an element which is related to a benefit, and that relationship is described by the score. And this is what it looks like. So remember, each one of those benefit keywords had two statements of benefits, right? So those two statements are these alt 1 and alt 2. So we have 2 for community, 2 for economy, 2 for environment. And these are the sigmoid scores for sidewalk, bike lane, and median. And then from there, we sum the values of the 2 alternative benefits. Those 2 alternatives are summed. And we do some cleaning up. Some sentences are not worth keeping, so we clean that up. And finally, we come up with 566 unique sentences for sidewalk, 310 for street buffer. So you can see how many times each one of those elements appear in. And then finally, we normalize it because we want to make sure that they all sum up to 100. And finally, we do an evenness check as well. And the reason we do this evenness check is because some elements actually are associated with multiple benefits. And if it's associated with multiple benefits, then we give it a higher value. So that is our evenness. It's essentially a Shannon entropy index. And based on that evenness, we also do the final normalization of those scores. So that's how we assign weight to our final scores. And the final thing I want to show is our website. And again, this is not complete, although okay. So the main part of the website that we want to show is this one. This is going to be the key, where you have the scores of each one of the elements and the composite score.
Sorry,
Yeah.
the webinar should be this website.
Oh, okay. How do I stop sharing and then share again?
Yeah, share the whole page.
Okay. All right. Share.
Yeah, bottom green button.
Next.
The green.
This one.
Mhm. And then do the
There.
top. Do the top left.
Can they see it now?
Yes.
Okay. So here you have, and if you point to any segment, you can see the composite score of that segment. And you can see the composite score, not the composite, the individual scores of each element as well. So for example, here you know what the size of the sidewalk is. POIs, whether there is a bike lane. As you can tell, there are very few bike lanes around. Medians, we only have a few. Street buffers. So, and I should also point out that the streets that we have selected to display here are the streets that ARC has designated as potential complete streets in Atlanta. So with that, I'm going to stop sharing this screen and go back to my original presentation, because I just have the final takeaways. So we now have ubiquitous data and tools to develop scalable and replicable approaches for documenting and storing roadway assets. Such tools will help us develop benchmarks and best practices for designing better street environments that are safe and welcoming for all. And developing comparable measures of roadway assets will help in creating better analytical tools for estimating how these assets can contribute to livability and economic vitality. And I'm done. Thank you all.
So we'll take questions either online or in person. So I've got some trustee students monitoring the chats, and any questions from the room at the moment come to mind? Yes.
Thank you for that presentation. I'll probably a couple of questions now, so my question first, like that. The highway capacity manual here. I think starting in 2016, they still sleep and then CM7 for research. They have a methodology for ranking of research.
Okay.
Which uses the same metrics that you're showing, but I think they don't have possible advanced data that
Right.
So thinking if you have any comments on the adequacy of because that's the state of practice, that's what the additional but I think ARC is saying they're of this with their own of this for so I don't know if you would have any comments on the adequacy or inadequacy for that methodology, and also how you see this more emerging data set methodology that will get you to practitioners to be able to rank.
Well, that's a great question. Thank you.
Can you repeat the question?
Okay. So the question is that the recent edition of the highway capacity manual has its own method of scoring complete streets. So how does our approach differ or add to that method, right? So as I mentioned early on in this presentation, that our method is based on ubiquitous data. That is data that is ubiquitous and therefore comparable across cities, at least in North America. And therefore, we are also providing tools by which you can quickly and scalably measure the different elements of complete streets without having to go out and do manual measurement of these. And if you look at the highway manual, they don't really provide any tools for actually doing that. They give you a scoring system, but how you bring the data to the system is completely up to the individual departments of transportation. And they may have different ways of bringing that data into the system. But we are providing a completely scalable and comparable approach across all cities.
How did you, or to what extent did you validate the scores for the complete streets? For example, like, did you do any like case studies of streets that you know to be very complete and then ensure that the score is reflected adequately?
We haven't done extensive validation of that yet, because that last part on scoring the completeness of street is very new. I saw it like 2 weeks ago. So we haven't done a complete validation of this. And there are a couple of elements that we are still adding. For example, we are still adding the medians and the vehicular traffic. I didn't even talk about the vehicular lanes. So that is another element that we are adding now. So it's not, our project is not complete, but we are well advanced to at least do this presentation. Yes.
Yeah, I'm just wondering if there's any DOT showing their interest to use the sport, and how do you convince them to use your sport to evaluate, and what's their motivation? They want to make this kind of evaluation.
Well, I know ARC is very interested, and they have reached out to me. UJ is now part of ARC, is in the transportation division of ARC. So he was involved in it right from the beginning. So they have been very much involved. And we haven't really taken it on the road. This is the first presentation that I'm doing of the entire project. You know, we've done some presentations just of the sidewalk or just of parking, but we haven't done anything like this with the entire, elements, all the elements included. So hopefully, when we have that validated completely, we'll take it on the road and share it with others. By then, we'll have all the tools on the GitHub, and people can very easily find the tools that they need to apply it in their own context.
Thank you very much for your talk. This is a very big project. I'm curious about two things. The first is, have you considered, as you, given the methodology that you're proposing for the index, have you considered that if you're basing the data on the reports on complete streets that have already been designed, that they might be incomplete in a sense, and then the score that is being produced is being built on biased data or like data that is incomplete?
So yeah, that's a good question. The reason why we don't have any concerns about that is because we are using those manuals only to find the weights for the different benefits. We are using it only to see how each element is associated with a particular benefit. And those benefits, I don't think are going to change. You know, those benefits are what we expect those benefits to be. So we are only looking at the association.
But as there are more reports generated and more municipalities develop complete street policies and handbooks or whatever, that could change your weights over time. You envision redoing that part of it every so often?
We could, although we don't expect those benefits because, you know, it's also, you know, we looked at it and it seemed reasonable. You know, we looked at which one has the highest benefit and which one is next. For example, sidewalk was rated the highest, and it seemed reasonable to us that that would be giving us the highest benefit.
And in a way, I think it makes sense that their reports would reflect the community's priorities and tell very well about the weight. I'm curious then, my second question is following up on that. What is the role of freight transportation? How do you see the role of freight transportation in the definition of complete streets? That is a concern that I always have as a researcher on freight. I see the various levels of completeness in the street, most of the time lacking freight to accommodate freight users. So I was curious if this is something you have thought of or have considered.
To be honest, we haven't. Particularly because it's a very thorny area. And freight, essentially, you're talking about small vehicles, small freight vehicles like Amazon trucks and other deliveries that are pretty much ubiquitous in every road. The large freight may not be going through all the complete streets. They might be restricted to certain kinds of streets. But yeah, we haven't really thought about freight.
Directions for future research.
I also have a question about the weight process, so I wonder, in your opinion, what, how much it would matter if the policies, if the complete street policies were created in-house by the city versus by a consultant. The reason that I say that is because oftentimes cities will consult out another agency or another company to create these policies for themselves, for them, and so then there's sort of a similarity in text across many of these policies. So maybe it's not actually reflective of the community's needs, but more of what the consultant has prescribed. I'm curious if you think that would make a difference. Is that a label worth considering in your?
We haven't really looked at whether there are differences between these two types of documents, in-house documents versus consultant-generated documents. We don't expect them to be, because usually consultants are supposedly working with in-house people, and there are in-house, representatives that are always providing inputs. So we don't expect the differences to be great between those two, but we haven't looked at those.
About the chat, do we have questions in the chat?
The first question we got from Elizabeth, it says, I'm curious about licensing of Google Street View. And if this is an explicitly allowed use, or if you have considered a use of other sources like Appleberry.
So we are concerned about that. And we've gone back and forth about what the license restrictions might be. We've even had Google staff who have come to lecture here, and we've asked a specific question. And we've sent essentially thousands of papers out there that are looking at Google Street View. They are not really too concerned about that. As long as it is not done commercial, that is, you're not doing this commercially. We did look at Mapillary. Their images are not as high quality, and they are much more spotty than Google Street View. So if you want to use ubiquitous data that apply for not just North American cities, but also European cities, and maybe some cities global south, Google is probably the best option.
Another question in the chat from Alex says, is it possible to talk about how holes in coverage are filled where images are blocked by trees or vehicles? Is an average condition assumed for that segment?
Yes, in fact, particularly for sidewalk width, there will be a lot of cases where you would have occlusion, which is why we do this 10-meter grid and then look at consistency even when there is occlusion, as long as we find a consistent width, we can join that and figure out where the two edges are.
A little bit of a longer one. If I can cover it.
And by the way, we'll be quitting at 1:15, so 3 minutes to go.
Okay. So this is a question that's based on Chandra's personal experience. Over the past year, I found myself kind of tripping rather than walking places where there are vertical ridges on the pedestrian pathway. So the surface is not smooth vertically. On a visit to the University of Leeds, one researcher we met told me that as we age, our perception of depth and peripheral vision reduces, so that we are not walking fast without looking down, that we do not seamlessly grasp vertical displacement. Is this something for established firmly? Is this part of assessing pedestrian friendliness? Have you done any work in that aspect?
We haven't, but that's a great idea. We felt that was a maintenance question sometimes. You have tree trunks or tree roots that create issues with the pavements becoming uneven. So there is a maintenance issue there as well. But it's important, it's absolutely critical, as Chandra points out, to know where these hazards are. And I've been part of another project where we had tried to crowdsource hazards using an app.
Last question. On the building up of Sophia's question, on the same token of freight and commercial deliveries, have you considered the issue of emergency vehicle access?
No.
Well, that was a quick answer. This question. I want to thank you. I'm sure we all want to thank you very much for an inspiring presentation. So.
Thank you all for listening. Great.
That's all for now.